Okay, so let's start. This is a week 11 session. Okay, so we will discuss a little bit of theory first. Can anyone tell me when is the deadline for week 11?
Next week, Wednesday, ma'am.
Okay, so today we'll discuss a bit of. Please mute yourself, everyone.
प्यार टमाटर काट दे
Okay, so in this week, we have very less theory. Basically, it is based on that DFS algorithm, graph traversal algorithm. So that's the main thing that is present in this week. So I will explain what DFS is, and we'll discuss a little bit of the algorithm pseudocode part. Then we'll solve the practice assignment. Okay. So before I start, I'm a little sick today, so please just try to listen carefully what I'm explaining at once. Okay, and please don't unmute and all these things. So let me share the screen.
Excuse me, ma'am.
Yeah.
Ma'am, can you please explain transitive closure once? I have a doubt in that particular topic from week 10.
What topic?
Transitive closure.
Transitive closure in CT.
Yes, ma'am. Ma'am, at the end of that second last lecture from week 10, actually, I watched the lecture, but I don't know, like, why am I facing problem in that particular thing? You could please explain that.
Same problem, ma'am. Yeah, I'm having the same problem.
See, week 10, I don't have the slides right now, but
Okay,
okay,
ma'am. No problem. You
let
please
me
continue
check
with what
once.
you're having.
Yeah, okay, I'll first complete whatever the week 11 stuff I have. Okay, then if I have
Yes.
time, I'll take up that lecture.
Okay, ma'am.
Okay, anyways, tomorrow also Piyush sir has a class, so if I don't get time to do that today, tomorrow he'll cover it. Okay, I'll tell
Okay,
him.
ma'am.
Okay,
No
ma'am.
problem. Please don't take.
Yeah, thanks. All right, so first concept here is recursion. So anyone has any idea what is recursion? You all know iteration, right? Any idea on what?
Calling the one procedure again and again.
Right. So following the same procedure. Anything else you would like to add? Like what are the different parts of a recursive function? Any idea? All right. Listen. My screen is visible, right?
No, ma'am. You're not sharing the screen.
Okay. No?
Yes, ma'am.
All right. See, recursion means that any procedure that we have, okay, if we call that procedure within itself, then that is called a recursive call. Okay, any procedure or any function that you're calling within itself, that is a function calling itself or a procedure calling itself, that is called recursion. Okay, now you know the factorial function, right? We have solved factorial with the help of iteration. So anything that can be solved with iteration mostly can also be solved with the help of recursion. The difference is that in case of recursion, we need a base case. All right. Even in your iterative method, we have a base case. Like when we say that while there are more cards in file 1, that is the beginning of the iteration. When will that stop? When your file 1 is empty. Right. So in recursion, the base case you have to define at the beginning. That if, like in factorial, you tell me, if I want to find 5 factorial, right? So 5 factorial means what? 5 into 4 into 3 into 2 into 1. Right. So what is the base condition where this will stop? I mean, where do we stop this? This is basically n factorial means n into n minus 1 into n minus 2, like this. Till what condition do we go on? Till we reach 1. Right. That means when I reach 0, that is the point where I'll stop, because we know 0 factorial is equal to 1. So this is the base case. So when we reach 0, we'll know that, okay, now it's the time to stop. So factorial is just an example of one such procedure that you can do with the help of iteration as well as recursion. Now, let's say this n factorial problem, okay. This n factorial problem, can I write it like this? See, this thing that I wrote, instead of writing this whole thing, if I write n into n minus 1 factorial, is this same?
Yes, ma'am.
Same, right? Now, instead of this, if I write n into n minus 1 into n minus 2 factorial, this is also same. So
Yes,
what we
ma'am.
are doing is, we are calling the factorial function again and again. Okay. So first, when I try to do n factorial, then I'll do n into n minus 1 factorial. That is, I will call the factorial function again, but this time I'm trying to find n minus 1 factorial. Then again for n minus 1 factorial, I will do n minus 2 factorial. N into n minus 1 into n minus 2 factorial. So this this procedure will be called again and again. Okay, that's a recursive call. So mainly recursive call means the function calling itself within itself. And recursive procedure will, if you call a function, wherever the function call is, the control will shift there, right? So if I call the factorial function, like say I am trying to find in this factorial function, trying to find n factorial. Okay, so n is the argument. Now inside this function, somewhere I have called factorial n minus 1. So the control will shift here, right? Then again inside this n minus 1 factorial, if I have somewhere called n minus 2, then the control will shift there. So until I reach the base case, the control will keep on shifting. Okay, and once I reach the base case, then the return statements will be issued. And this all sounds a bit confusing, but let me take the example. So this recursion or this concept of recursive call, this comes from inductive definitions. Okay, which means many computations are naturally defined inductively. That means there is some base case that is directly return the value. In case of factorial, the base case, like I told you, is 0 factorial, because we all know 0 factorial is always 1. This is constant. This is the base case. Inductive step is compute the value in terms of smaller arguments. So like I said, n factorial, we divide this into smaller parts, n into n minus 1 factorial. Again, we divide this into another smaller part, n into n minus 1 into n minus 2 factorial. So these are all same, right? All of these mean the same thing, but we are just dividing the problem. Okay. See, n factorial means this thing, n into n minus 1 till 1. 0 factorial is defined to be 1. This is the base case. So when I call this factorial procedure and I put 0 as the argument, then it will always return 1. Now, for any n that is greater than 0, factorial n will be what? N into factorial n minus 1. Is this part clear for everyone? Anyone has a doubt that why I am writing factorial n equals to n into factorial n minus 1?
No, ma'am.
Right. So same thing. Now, if I write the procedure for this, so let's say factorial is the procedure name. I'm putting n as the argument. So this n can be anything, right? Even I can take 5, for example. Now I will check if n is 0. That is, first you have to check the base case. If n is 0, then I will directly return 1. I won't do anything else. If n is not 0, then I'll go to the else part. Else part is doing what? Return n into factorial n minus 1. So as soon as I come to this return statement, where will the control shift? To this part, this procedure call, right? Now this procedure call, when I go here, what will be the code? Now just there will be a call of this factorial procedure with the argument n minus 1. Again, same thing it will happen. We have to check if n minus 1 is equal to 0. It is not. Let's do for 5. So first, if I take 5 as n, 5 is not equal to 0. So it will be what? 5 into, return 5 into factorial 4. Right. Now when I call factorial 4, then inside this procedure call, what will happen? Again, check whether 4 is equal to 0. No. Then come to the else part. Again, return statement will be what? 4 into factorial of what?
3.
3. Again, come to this part. Control will shift here. Wherever procedure is being called, control will shift there. Then again, return 3 into factorial of 2. Again, control shifts here. Then return 2 into factorial 1. Now control shifted here. Next, again check 1 is not equal to 0. So again return statement will be issued 1 into factorial of 0. Now when the control shifts here, so the base case I will check first. Is 0 equal to 0? Yes. So I will issue the return statement. That means this part, this part of the return statement, this will return what?
1.
It will return 1. So now what does this evaluate to? This entire return statement? 1 into 1. That means it will evaluate to 1. Where is this 1 value going? Where this was called? Where was it called? Here. In factorial 2. Right? Wait, this is factorial 3. This
2
one
into
was called here.
factorial 1.
Right? So this now becomes 2 into 1. So return 2 into 1 means return 2. This statement was called where? Here. So this now becomes 3 into factorial of 2 is returning what? 2. So 3 into 2. So return 6. This 6 will be returned where? Here. This becomes 4 into 6. That is 24. This 24 is returned here, where factorial 4 was called. So this becomes 5 into 24. That is 120. And this is the ultimate value that we are looking for. This will be the final return value. Is it clear how the procedure is being called? Any question, anyone?
Why we can't give n factorial directly? Why we are splitting it into n into factorial n minus 1?
You can do it in iterative way, you can do it in recursive way. Iterative way we have seen before, this is the recursive way of doing it. So recursive means we will call the same function again and again by splitting the problem into smaller parts.
Ma'am,
Okay.
what is the advantage of using the recursive way?
Recursive way will take a less amount of time. Because as soon as the return statement is issued, the value will go back to the previous one. Iterative way will take more time. Recursive way is faster. Anyway, there are some problems which we always require recursion. Like that is not possible to do with iterations. We'll take those examples. Okay, this is just one example where you can do it both ways. But is it clear how the recursive call occurs or how the return statement is issued?
Yes,
So
ma'am.
wherever the base case is met, right, that value will be returned immediately to the previous return statement. Then again that value is evaluated, again returned to the previous return statement till you reach the original function where you started the recursive call. Okay, the parent function. Then you will return the actual value.
Excuse me, ma'am. Can you please give some more examples where only recursive way will be used? Like this is one of the.
Yes, we will come to that. Okay, there are questions on that. Wait. Must understand what is recursion, because if you don't get this, then you won't understand why we are learning this is because of depth first search. So that is the biggest example of recursion. That thing you cannot do. I mean, using iteration, if you can try yourself, if you can write a function for depth first search. So for that you need to use recursion. Why? Because we are coming back to the same point again and again. So when I define what is depth first search, you'll understand that. Till then, just wait a little. So this is the function. Okay. So factorial n is suspended till the factorial n minus 1 returns the value. So that means every time in the return statement we see a function call, we suspend the rest of the function, right? We suspend the rest of this function and go to directly this call. Then again, in this call, when we are again calling the recursive function for n minus 2, that function is suspended and we go directly to the n minus 2 call. So when are we coming back? When the return value is evaluated. Then we will trace back. So there is a lot of backtracking in case of recursion. Right. So see, this example is also good. So this is based on lists. Okay. So base case is an empty list. Now inductive step is what? Compute value in terms of first element and rest. Okay. So I want to find the sum of numbers in a list. Okay, let's say this is my list. 1, 2, 3, 4, 5. This is my list. Okay. This is L. Now I want to find the sum of all these elements using recursion. So how will I do that? First, let's initialize an empty list. Okay, if L is initially empty, they're saying. If L is empty, this is the base case. Then sum will be what? 0.
0.
If it is empty, no sum. So sum is 0. Otherwise, this is base condition. Okay, like in factorial, we had 0 factorial equals to 1. That was the base condition. So here, this is the base condition. Otherwise, if there are elements present, then add first of L to the sum of rest of L. So how that will work? See, this is the actual procedure. Okay. So I am passing my list 1, 2, 3, 4, 5 here. Okay, 1, 2, 3, 4, 5 I'm passing here. So this list, is it empty? No. So I'll come to the else part. So return first of L plus list sum rest of L. So list sum is this procedure name only. So it is a recursive call. It is calling itself. First of L is what?
1.
First element.
So 1, right? List and list sum rest of L will be calling this function only with what list as argument? 2, 3, 4,
2,
5.
3, 4, 5.
Right? Now again run this procedure for this argument. So is list empty? No. So next return statement will be what? First of L, now it is 2 plus list sum. What is the argument? 3, 4,
3,
5.
4, 5.
Now next call return statement will be 3 plus list sum argument 4, 5. Right. Next. This part. So return statement will be. You tell me what will be the return statement. Next step.
Return 4 plus list sum list of 5.
This. Right. Now this one. For this, what will be the return statement?
5 plus empty list.
5 plus list sum and an argument I'm passing an empty list. So now when I evaluate this, base case will be satisfied, right? Because list is empty. So this part will return what? This bit
0.
0. So 5 plus 0. So this return statement will return 5. Where will it return that? Here. Then this return statement will return what? 5 plus 4.
9.
So 9. That will be returned to this one. Now this will return 3 plus 9, that is 12. 12 will be returned to this one. Now 2 plus 12 is 14. That will be returned to the original call. So 14 plus 1 is 15. This is the final return value. right? So basically, what you have to understand here is that every time the recursive call is there, you have to keep on shifting the control to that return statement. Okay, that part of the procedure call. And once you reach the base case, then you will start evaluating. Once you start evaluating, you will start backtracking. This go back to the previous return statements until you reach the parent function. Clear?
Yes, ma'am.
See, this same procedure can also be done by doing last and init, right? So instead of doing first and rest, if you do last and init, so just take the last element and then keep on decreasing one element from the end of the list, right? So you can do this using first and rest or last and init. So in that case, if I pass 1, 2, 3, 4, then this will be last of L. So 4, and then list sum. Argument will be what? 1, 2, 3. Okay. For this, again, return statement 3 plus list sum
1, 2.
1, 2. Again, for this part, return statement will be
1 plus list of,
2
sorry,
plus
2 plus list of 1.
2 plus init of 1, init of this. Because last element I'm eliminating, no? So I'll do init. So this. Again, for this part, return statement is
1 plus
1 plus init of 0. Like
1 plus
it is
list sum empty list.
empty.
Now this will evaluate to 0. This 1 will go here. Again, this 3 will go here. 7 will go ultimately here. Or no, this is 6, right? 6. So 6 plus 4, then 10 will be the ultimate answer. Okay. See, recursion is very easy, okay, once you're accustomed to it. Same thing we can also do for insertion sort. So
And
insertion
once could
sorting,
you go to
everyone.
previous page, ma'am?
Yeah.
Thank you. Yeah, you can go to the next.
See, insertion sort procedure, we all know, sorted list insert. What do we do in insertion sort? You don't have to go through the entire thing now. Insertion sort, we take first think that we have a sorted list. Now in that sorted list, if I want to enter some element X, then using insertion sort, I can insert that element X into its sorted position, right? And we have that procedure called sorted list insert. So we have to use that. So even this sorting, this can be done using recursion. So first we have to build up a sorted prefix, extend the sorted prefix by inserting the next element in the correct position. Let's see how this is. So this is the procedure insertion sort, right? We have a sorted list, which is an empty list initially. Now for each Z in L, right? So let's say our L is some list, 2914. Okay, let's say this is the list. So initially sorted list is empty for each Z in L. This sorted list insert this procedure you're calling. So sorted list will call. Where is the recursive call here? So sorted list is that empty list inside which we are calling sorted list
Sorted list
insert.
insert.
Okay, where we are giving sorted list as the argument. So this is the basic procedure that we have seen till now, right? Now, what if I want to do this in a recursive way? So this is insertion sorting basically. Normal insertion sort code, right? And everyone knows this code. Do you want me to explain this? Anyone? If you want, I can explain. Anyone? Okay, see. So sorted list insert is a procedure where we take a list L, okay, like that list I took 2914. This is L list. Now let's say I want to insert the element 3. So X is 3. So both of these I will pass as argument here. Okay. Please mute yourself. Don't do this today, okay? All right. See. So this is my list that I'm passing as argument, and this is the variable that I want to insert. X is the element that I want to insert in this L list. So new list, the screen is visible, right?
Yes, ma'am.
Yes, ma'am.
Okay. So new list is an empty list. Okay. Inserted is a variable that we will set to false initially. Now for each z in L, what is the first z?
2.
2 is the first z. So for each z in L, if not inserted, when will this be true? Not inserted, when will it be true? When inserted is
False.
false. So initially inserted we set to false. So this will be true. So I will enter this if block. Now we have to check if x is less than z. So x is 3 and current z is 2. So is 3 less than 2? No. So I will not enter this one. Instead what I will do is, so this if ends here and this outer if ends here. So new list plus plus z. That means in the new list that was empty initially, I will enter the current z. So new list has what now? 2. Okay. So see, look at the curly braces very carefully. This if is ending here. Okay, and this outer if is ending here. This for each block is ending here. Okay. So after you insert z, then again go back for the next z. What is the next z?
9.
9. So inserted is still false, right? So not inserted is still true. Now is 3 less than 9? Yes. So in new list, you will now enter 3. So new list becomes 2, 3. And inserted variable is now set to true. Okay. Next. So after that, so this if ends here, right? So I will go for the next one. So what is, wait 1 second. Yeah, okay. So after I insert 3, will this statement be issued?
Yes, ma'am.
So what is the current z?
9.
So that will be added to new list. So this should become 239. Is this correct? Okay, let's
Correct,
see.
ma'am.
Okay. So 239 till now. Okay. Now let's go for next for each. So next Z is what? 1.
Excuse me, ma'am.
Hmm.
Can you please repeat this step?
See, you understood after I inserted 3. So this one where 9 was the Z, not inserted was true because inserted was false. We checked whether X was less than Z. So X is 3. 3 is less than 9. So in new list, I will append X. Okay. So new list had 2. Next I appended 3. So it is now 2, 3. Inserted variable is now set to true. Okay. All of this is done.
Yes,
Now
ma'am.
come to this new list and append the current Z. Current Z is 9. So it became 239. Alright. Now inserted has been set to true. So for next for each block, for each iteration, what is the next Z? That is 1. So is not inserted true anymore?
No, this is false.
Inserted is true. So this is false. So what will I do? This iteration will not work. So after this, tell me, will not inserted ever be true again?
No, ma'am.
No, right? So next I will come to this statement. Like for each is closing here. Okay. Next I'll come to this statement. But this is also if not inserted. But inserted is true now, so not inserted will again be false. I think something is wrong. Wait.
Ma'am, but
Insert 1 in that line, new list is equal to new list plus plus Z.
Yeah, that will happen. But for the next one, for 4,
Again,
These two will not happen. I will directly come to this line. So
yes,
after
ma'am.
9, I will insert 1.
And then 4.
And then for next Z, it will be 4, but not inserted is false. So none of this will happen. Again, directly come here. So it will be 2, 3, 9, 1, 4. But this isn't sorted.
Because you
We have to
passed
check.
the unsorted list, ma'am. That's
Because
why.
I passed unsorted list, right? I have to pass a sorted list here. This procedure only works for sorted list. So sorted list insert will only work when L is sorted. Then the new element that you are entering, that will enter in its proper position. So if this list, let's take a sorted one.
Initially, we have to take sorted list, ma'am. Like 1, 2,
Yeah, insertion sort, initially we will think that we have a
4,
sorted
9, I guess.
Yeah. Then in that sorted list, if I want to insert something, it will be inserted in correct position. So if I
Yes,
take this
ma'am.
list, right, now if X is 3. So for first iteration, let's do this again. So first Z is what? 1. Inserted is false, not inserted is true. X is 3. 3 is less than 1. Right? So new list, X will be inserted. 3 is not less than 1. So this will not happen. No? I won't enter this block. In new list, what will I insert? The first Z. The new list will have 1. Next, for next iteration, what is the next Z? 2. Is 3 less than 2? No. Again, I will come to this part. Insert 2. Next is 4. But 3 is less than 4. So new list will be inserted with 3. So 3 will come here. Inserted will be set to true. Next, come to this line and insert the current Z, that is 4. Okay. Next iteration, Z becomes 9. But inserted is set to true 1. So this will never be true again. Not inserted will always be false. So directly come to this line again. And add 9 to new list. So now this is a sorted list, right? So this list will be returned in return new list. Okay, this procedure is clear?
So this only works with the sorted lists.
Yeah, so the argument that we are taking, this list will be a sorted list. And I am trying, actually insertion sort, what happens that we know that we have a sorted list and we want to add some element into that list. If I want to insert some element into that list, then using this procedure, the element will be inserted in its proper position. Okay.
Okay, ma'am. What if we have to go with the this will be valid for both ascending and descending order, na?
Yes. But for that you have to change the condition. I think for that this condition has to be changed. But the basic procedure will remain same. You just have to check for that greater than less than thing.
Okay.
So insertion sort, now this is the basic procedure. Now if I do it inductively, that means if I do a recursive call on this. So list of length 1 or L or less is always sorted. So if I have one element in my list or if it is an empty list, that is always sorted, right? One element list means it is sorted. For longer lists, insert first of L into the sorted rest of L. So why is this written list of length 1 or less is always sorted? This is our base case. Okay. So we will keep on diminishing elements from the list until we get a list which is of length 1. So we can say that this is a sorted list. Now I will again add the elements as I backtrack. Okay, this is the concept. So see, procedure insertion sort I. This is the same procedure that we just saw. Okay. Now this procedure we will call inside this insertion sort L. Okay, this L is the sorted list. Now if length of L, let's say this same list, let's take 1294, 1249. Okay. So let's take 1249. This is L. So what is the length of this?
4.
4.
So 4 is less than equal to 1? No. So I will go
No,
to
ma'am.
else part. else part will have a return statement. You should see mainly all recursive procedures look the same way. Okay, you have an if statement first, which checks the base condition. If base condition is true, you have a return statement. If it is not true, then else part also you have a return statement where the procedure call is present, recursive call is present. This is the basic structure. So here also see else part return statement. Inside this you are calling sorted list. That is sorted list insert. There is this procedure. And what are the arguments you are passing? What is the sorted list you are passing? So we are taking the first element out. Okay. So insertion sort rest of L, right? And first of L. So these two are we are taking as argument. So insertion sort rest of L, this is the recursive call, right? So control will shift here. So if I do insertion sort rest of L, what will be the next part? Now L becomes what? In this recursive call, what is the L?
It will contain one element.
It will be 249,
249.
right?
Hmm.
Again, length is 3. So it will again come to the else part. Base condition is not satisfied. Now you will call this procedure again, this return statement, and inside this sorted list insert. Inside that you have the recursive call insertion sort. Now rest of L gives what? 4, 9. Again length is 2, which is again not satisfying base condition. Again come to else part. So return sorted list insert. What is the argument? Insertion sort rest of L. So now rest of L is what? 9. Right? Now when I come to this part, now when I'm calling insertion sort rest of L with this 9. So what is the length of this? 1.
1.
That
One.
will satisfy my base condition. Right? So this will return what? The list itself. Right? It will return just this 9 because base condition is satisfied. Now go back to previous call. The previous call had sorted list insert. I'm writing SLI. Inside this, the argument was passed as insertion sort rest of L, where this was the rest of L. 9. Okay, and this returned the 9 only. So 9, and what is the first of L that was here? What was the first? 4?
1.
Just before this. What was the first element? 4, 9. So
4,
4 was
4.
the first, right? So
Yes,
4.
ma'am.
So now using sorted list insert, I am inserting 4 into this list. So once this is done, what will be the sorted list? 4, 9. Now this will go back to the previous call again. So what was the first in that? 3. I'm sorry, 2. So 4, 9 and 2. So I am trying to insert 2 into this 4, 9 list. So again 2 will come in its sorted position, 2, 4, 9. Now go back to the previous call again. So 2, 4, 9 is now the first element, first argument. What is the first of L that we had? 1. Right? So now what will be the list? 1, 2, 4, 9.
Right.
Now parent function, that was the first recursive call. There the first was what?
9.
So we already finished, right?
Yeah.
1, 2, 4, 9. This is what we had. So see this insertion sorting, this thing, we can do it just using this sorted list insert procedure. We're calling this procedure again and again, and inside the procedure, see here it is a little tricky. Why? Because the recursive call that is happening in the form of an argument. Okay. So I think this part, maybe some people are confused, right? Should I explain this again?
Ma'am, I'm not getting
Ma'am,
idea that we have already taken the sorted list. Again, we are sorting that back.
can
Like we
we
are getting
do
the
it
same.
using a ma'am
No,
unsorted list?
actually, why we are doing this part is, see, this sorted list insert, if I directly do it, this is fine. Okay. But now we want to do this in an inductive way, that is in a recursive way. So how can I do that using recursion? For that, we have this procedure. So, okay, you want to do this using what?
And
Unsorted
unsorted list.
list.
Yes, ma'am.
Okay. Okay, let's take 2914. This is the list. Let's take 9.
Okay, ma'am.
Cell. Length is 4. So first, this is not satisfied. Come to else part. I will write the return statement this time. Okay. The first return statement. Return sorted list insert. Inside this, I have insertion sort. I'm writing IS. Rest of L. What is that?
914.
914. And what is first of L? That is the second argument. 2. Right? This first element. So this is the
Yes,
first
ma'am.
call. Now inside this, again, control will shift to this insertion sort 1. So now the second call will return. Again, the length of this list is 3, so base condition is not satisfied, so come to else part. Now second return statement will be sorted list insert. Inside this, I'm calling insertion sort. And what is the argument this time? Just take out the first element.
1,
So this
4.
will be 1, 4. And what is the first?
1.
9,
9.
9.
Ma'am.
Now again, control will shift here. Yeah.
Okay, ma'am. Okay, ma'am.
Okay, see, this 9 is coming out.
Okay, ma'am.
So now control is shifting here. Again, same recursive call, but length is 2, so base case not satisfied, come to else part. The third return statement, sorted list insert. Inside that, the argument is insertion sort. What is rest of this?
List of
Just
4.
4.
4.
And first is
1.
1.
1. Okay. Now, again, control shifts to this part. So length of this is what? 1. That means base case is satisfied, right? So this part will return what? L. L is what? Just this 4, right? So just this 4 will be returned. So SLI, that is sorted list insert, inside this during backtracking. Now we will have, let me write it this way. Now we will have just this list 4 as the argument, right? Because this was returned here since the length became 1. So the list itself is returned. So that will come here. So now sorted list insert, if I have this list and this element as 2 arguments, what will this sorted list insert procedure do? Insert 1 into this list.
Yes, ma'am.
That is what it does, right? So after this, what will be the return value from this third call? 1,
List
4.
of 1, 4.
That will be returned where? Here. So
Yes, ma'am.
now this becomes 1, 4. So sorted list insert 1, 4 is the list and 9 is the element. So now 9 will be entered in its sorted position. So from the second call, we will get back 1, 4, 9. Okay. This will go back where? In the first call. So now sorted list insert 1, 4, 9 and 2. So now 2 will be inserted in its sorted position and finally we will get 1, 2, 4, 9. This sorted list, this will be returned as the return value of the parent call. That is the first call of the procedure. Is this clear? Any part you didn't understand, tell me, I'll explain again.
From the third set. So after we
Third
length
one, right?
is yeah. From
So
there
initially, what did we have? See, here in this, I had insertion sort within which the argument was 4. This list, right? So when control shifts here, the list has only one element. So what is the length?
1.
1. So I am calling this procedure the insertion sort. So if length is 1, it is satisfying the base case. If base case is satisfied, then what is the return value? Return L. That is what you passed as argument. What did you pass as argument?
4.
This 4. So this 4 only will be returned.
Yeah.
right? So now here I can write just this 4 and comma 1. This 1 was already there before from the first element that we extracted. So now sorted list insert, this procedure is being called. So inside this list, I have to insert 1 in its proper place. So after that is done, the return value will be a list like this 1, 4, right? This 1, 4. This will be returned to the previous call here. So once 1, 4 is returned, now the length is
2.
what? 2 again, right? So this 1, 4 is returned here. That means now instead of writing this, I will just write 1, 4. 1, 4, and I want to insert 9. So sorted list insert will place 9 in its proper position in the list and it will give back 149. Where is this 149 value returning? Here.
Last.
So 149 will come here. This will be 149 and 2. So this L is 149. Okay. And this X is 2. So now 2 will be inserted in its proper place. So it will give rise to
Okay.
1249, which is the final
Got
result.
it. Got it.
Okay, so there is just a lot of backtracking. So until you reach the base case, you keep on calling the function, recursive function. Keep on calling it till the base case is satisfied. Here, base case is when length of list becomes 1. Okay, or less than 1. That is the base case. Once that is satisfied, then you will start the backtracking. Okay, and the return values should go one step back at a time. So just take care of that after third step, whatever the return value is, that will go back to the second step. Then perform whatever operation is there, again evaluate it, return value will go back to first step, like this, just backtrack. Okay,
So
so
initially it is making us a tree and then it is backward and adding
yeah,
this
you can think of
procedure.
it like that. That first
Yes,
I'm
yes.
just
Just
going
segregate everything one by one.
right, and then again I will backtrack to the previous
Yes,
step.
yes. Got it.
Okay,
Ma'am,
until I reach the base one. Yeah.
The
ma'am, for
return
the
part is happening in the first step, right? If length is less than or equal to 1.
Yes. Once this base case is satisfied,
Yes.
then only the first return value will occur.
Yeah. After that,
Then this return value will go back to the previous return statement, the second one. Then evaluate it again, it will go back to the first one. Here it is a little bit complicated. Why? Because the recursive call itself is happening inside a function call. This sorted list insert is a normal function call. Inside this, as an argument, the recursive call is present. That's why it's a little difficult to understand.
Yes,
So
ma'am.
when I'm reaching the base case, then this return L is coming inside this sorted list insert call. So here the 4 is coming. Instead of writing this, I'm going to return just 4. And the first of L, that was 1.
you
Okay.
need to say after reaching the base, return L will be going to the return statement in the else part. That
Yeah,
function
whatever is the last return call, it will go back there.
in the
Once
else
the base,
part, right?
yes, in the else part. See,
Okay.
this is the basic structure of any recursive function, that first the if statement will have the base case. Okay,
Okay.
and the else part will have that if the base case is not satisfied, then you come here and have the recursive call. So you will keep on calling recursively until some recursive call will satisfy the base case.
Okay.
Once that is
This is the
satisfied, then
structure.
then you issue that return statement, this one.
Okay.
Then just backtrack.
Okay. That means it is not completing in the first return L. It
No,
will
no, no.
again come to the else part in that function.
Yes,
And
yes.
insert, calling the procedure again and again and inserting, right?
Because what happens, see, once we issue a return statement, right? So once I had this first return statement, then I had this sorted list insert. Inside that, I call this insertion sort, right? This was the recursive call.
Yeah.
And I shifted the control here.
Yes.
So I shifted the control here, but the program was, this procedure was not done executing, right?
Yes.
So I will come back to it again.
Okay. So these one by one elements in the list will be stored separately as return value.
Yes.
And it will be
Everything
sent
will
to
be
the.
stored. Yes, everything will be stored. Just the return statement has to backtrack.
Okay, fine. Thank you.
Okay. So, see, I will say that this is a difficult example to understand recursion. Factorial is the easiest example. But you now understand how recursion works, right? So if
Yes.
this is
Yes.
clear, then only I will go to DFS. If anyone has any doubt, you ask now.
Ma'am, could you show the last page, like the insertion shot? Just 2 minutes.
This is very messy.
Yes, ma'am, over here.
Ma'am, here in the base case, I could
Yeah.
have written length L equal to 1. That would
Yeah,
have
yeah.
worked fine, right?
Yeah, sure. Yes. It would have worked.
Okay, ma'am.
What did he tell, ma'am? What was his idea?
Come again?
W- just now someone has said something like
Yeah, he
what
said that instead of
was
less than equal
his
to, we can
idea?
also write equal to 1. That's what he
Okay.
asked.
Okay, ma'am.
Okay, so that will also work here. Now let's do the DFS. So this is just you need to know this as a precursor to DFS. Mostly questions will come from DFS only. Okay.
Over there was once we found the length as 1.
Yeah.
So we are returning that value and we are inserting. So again, it's going to the else part, right?
Yeah, it will trace back to the last call. The last call was
But
made in the else part only, right?
however, already I returned. Again, also it is showing. Again, also it is returning, right? One more.
Yeah, it
But
will
as a
keep on
procedure, it
returning till
will.
you reach the base,
Okay.
till you reach the first call.
Mhm.
It will
Okay.
backtrack from the last call where the base case is satisfied. That is where the first return value will be returned. Then you have to keep on evaluating and returning back to trace back to the last call until you reach the parent call. Okay.
Yeah. Okay, ma'am.
See, let me explain DFS. This is a very easy example. Okay, then it will get clearer. See. So we have graphs, right? So a graph can look like this. So I can say this is a graph. Can I say? Yeah. Now in this graph, I can trace from any node. Starting from any node, I can traverse the graph. Okay. So graph traversal, there are two types of algorithms. One is breadth first search, one is depth first search. We only have DFS in our syllabus, but I'll tell you what is BFS also in just a brief. So BFS is when you come to look. Let's say this is the graph. Now you want to do a BFS algorithm. That means you will come to this node. Let's say this is node I. You will start from here. You will explore all the neighbors of node I. Okay, so you will explore this. Then you will take up any of these nodes and explore all the neighbors of that node. Let's say I take up this node J and explore all its neighbors. Okay, so then I will, once I have exhausted this, then I will again go back and trace this node. Let's say it's K. I'll trace all its neighbors. Then this is exhausted. I will go here. Let's say L. Then I will trace its neighbors. So now, like this, all of the nodes are such, right? This is BFS. BFS means breadth first. That means once I reach a node, I will traverse all of its neighbors in one go. Okay. Depth first search is what? In this same graph, if this is the graph, I start from this node. Depth first means I will take one neighbor and explore that neighbor. Okay. Until I reach such a node which doesn't have any neighbors. So if I start from node I can go to any of these three. Let's say I go to this one, this neighbor. This is, let's say, J. Now I will not explore all neighbors of J. I'll just go to one neighbor first. Let's say this is K. Okay, now does K have any neighbor further or any child?
No, ma'am.
No.
No, ma'am.
No.
From K I cannot go anywhere. So I will trace back to J again and check what is the other neighbor of J. This one. Right? Let's name it L. So again, L doesn't have any more nodes connected to it. So I will again trace back to J. Now, have I explored J fully? Is there any other node that is connected to J?
No.
No.
So I will trace back to I again. So I has already explored this J neighbor and everything that was connected to J. So what is the next neighbor? This one. Okay, let's call it M. So it will come to M now. Now M has again two neighbors. Let's say N and O. So from M, first we will come to N. Okay. Then N doesn't have any more nodes to explore. So I will trace back to M and see what all is left to explore from this node. So O is left to explore. So I will explore O. Then nothing else is left to explore from O. So I will again trace back to M. Now everything has been visited from M. So again trace back to I. I has any more neighbors left that are not visited? This one. Let's call it P. So it will now come to P. Now P has any neighbors? Yes. Let's call it Q. So it will explore Q. Now Q doesn't have any more neighbors to explore, so it will trace back to P. So P has also exhausted all its neighbors, so it will trace back to I. Now does I have any other neighbor that I haven't visited?
No, ma'am.
So this is depth first search. This is a difference. Okay. So in breadth first search, I explore all the neighbors of a given node at one time. But in depth first search, I will go depth wise. That means I will keep on going to the next neighbor until I reach such a node which doesn't have any neighbor. Okay. This is the basic concept of depth first search. Now, how does recursion come into play here? We'll see. See this one. So first, the first question that we ask is, what are the vertices that are reachable from node I? So start from I, visit a neighbor J, like we did. Suspend the exploration of I. So after that, I will not explore I will explore J now. So explore J, continue like this. So let's say when I'm exploring J, I find a neighbor K. Now I will suspend the exploration of J and explore K now. So like this, I will continue until I reach a vertex which has no unexplored neighbors. Okay. Then I will backtrack to the nearest suspended vertex. So let's say from J, I went to some other vertex K. Now K doesn't have any unexplored neighbors. So I've exhausted it. So I will come back to the last suspended vertex, that was J. Like I just traced back. Okay, this is how you will do for DFS. So backtrack to nearest suspended vertex that still has an unexplored neighbor. This is the part, right? Now you can correlate. So we were backtracking when we met the base case. So here, what is the base case? When there are no more neighbors to explore. That is the base case. When that happens, then you backtrack to the previous one. Can you relate?
Yes,
Is
ma'am.
it
Yes, ma'am.
understandable? See,
Yeah, I have understood.
good. See, I'll take a graphical example. On that, you will understand better. So base defined. So this procedure, now someone was saying, right, that give one example where you cannot use iteration. So can you write this procedure using iteration? It is very difficult to write that because you have to keep a track of what is the last visited node. Now this information can be done recursively. I can keep track that what is the last recursive call. In iterative way, it is very difficult to do that. So this is best defined recursively. Maintain information about visited nodes. So what we will do is we will have a dictionary called visited. Inside that, we will maintain all the information about the nodes that have already visited. Okay. Now we have to recursively keep on updating this visited dictionary each time that we explore an unvisited neighbor. Okay. So first let me show you the graph representation, then we'll do the pseudocode. Otherwise you'll get confused. Or do you want me to do the pseudocode first?
Graph.
See, graph I will tell you, okay. Just I'll tell you how to do this, but I won't be explaining this side, whatever is written here. This you will understand when I tell you the pseudocode. So see, just look at this diagram, okay. If I start exploring from node 4, okay, I'm starting from node 4. So when I am starting from node 4, what are its immediate neighbors? Which nodes? Tell me.
1,
8
8,
and
1,
1.
5, 1, 5, and 8.
5.
1, 5, and 8. So these are my three possibilities. So let's say I start exploring 1. So from 1, where can I go?
2, 3.
2 or 3.
So let's say I take 2. So from 4, I have visited 1. From 1, I have visited 2. Now from 2, can I visit any more nodes?
3,
Yes.
ma'am.
3.
3. So from 2, I have visited 3. From 3, can I visit anything else that I have not visited yet?
No,
No.
ma'am.
So what is the last trace back? Where will this trace back to? 2.
2.
Now does 2 have any more neighbors left which are not visited?
No.
No, ma'am.
So trace back to 1.
1.
1, does it have any more neighbors left which are not visited?
No.
No.
So trace back to 4. 4 has any neighbors left not visited? 5 and
5.
8. So let's go to 5 now. Next I'll go explore 5. From 5, where can I go?
6.
Directly
6 and 7.
6 and 7. So let's explore 6 first. So if I go to 6, from 6, where can I go?
8,
8
7.
and 9.
7, 8
8.
and 9.
Yes, ma'am.
So 8 is already visited. I'm sorry, no, 8 is not visited. So let's take 7 first. Okay. If I explore 7, from 7, can I explore any node which is not visited?
No.
No, ma'am.
So trace back to 6. No, 5 is already visited, no? We started exploration from 5 now. From
Yes.
5 I came to 6, from 6 I came to 7.
Yeah.
So it is exhausted. So trace back to 6. From 6, can I go to any more nodes that are not visited?
8.
8 and 9.
8 and 9. So let's go to 9. If I go to 9, from 9, can I have any more nodes which are not visited?
8,
8
10.
and 10.
So let's go to 10. 10, is it exhausted? So trace back to 9. Now from 9, I can again go to 8. So let's go to 8. From 8, can I visit any more node which is not visited?
No.
No, ma'am.
So again trace back to 9. 9 has also exhausted all its neighbors. So it will trace back to 6. So from 6, any more neighbors which are not visited?
No,
No.
ma'am.
Everything is exhausted. Exhausted.
Now from 5, also everything is exhausted. So trace back to 4.
4.
Now all the nodes are visited. Got it? This is DFS. Now we will do the pseudocode. Just a second now.
Ma'am, we can start from any node.
Yeah, any node you can start from.
Okay.
Okay. See, any node why we can start from is because we are maintaining this visited dictionary. So that will keep track of all the nodes that you have visited. Okay. So it doesn't matter wherever you start from, it's okay. Now, maintain information about visited nodes in a dictionary called visited. So we have to recursively update this visited dictionary each time we explore an unvisited neighbor. So this dictionary will basically look like this. Visited. So key value pair, right? Let's say 4 is the node we started from. So once I start from 4, once I know that I am exploring this node right now, so I will make an entry in visited dictionary as 4 is to true. Now from 4, if I go to 1, so now I am exploring 1. So I have to make another entry for 1. 1 is to true. So every time we reach a new node, we will make an entry in the visited dictionary so that it says that I have visited this node. Clear?
For this such, we should make a list visited and then all the name of nodes.
It will be a dictionary. I'll show you why. Wait.
Okay.
To explore vertices reachable from I, initialize visited as an empty dictionary. Okay. Now visited will be updated how? Visited equals to DFS graph visited I. Like this we will write. So if visited dictionary looks like this, 4 true, 1 true, that is whatever vertices we have visited, those are marked. So what will be the keys of this visited dictionary?
Nodes.
Set of nodes that we have already visited that can be reached from I, right? See, this is the procedure. Procedure is called DFS. We have three things in the argument. One is the graph, one is visited dictionary, one is the node that we are searching currently. That is I, the node that we are exploring currently. So this graph is in the form of what? A matrix, right? So nodes and edges. That is in the form of a matrix. How do we represent a graph in the form of matrix? Everyone knows.
That adjacent
Yes, ma'am.
matrix
And
table.
basically, so
Ah,
V1, V2 like this. Here also V1, V2 and 0, 1. Wherever there is an edge, there will be a 1 value. So that graph, initially, whatever graph that we have where we want to perform the depth first search, that graph we will pass as argument. Visited dictionary we will pass and the node that we are currently exploring will pass. Okay. So let's say the first node that we explored in that graph was fourth node, right? So I is 4. So visited I will be set to true. That means visited dictionary, now I have created a key for I and set it to true. So 4 is now set to true. Now, what do I have to check? That where all can I reach from 4, right? Which all nodes can I explore from 4? That means I have to go through all the other nodes. So for each j in columns of graph will give me a list of all the nodes, right? Columns and rows, they have all the nodes, correct?
Yes, ma'am.
So I can, using this for each block, I can traverse through all the nodes in the graph. So for each j, so I will check for every node, is there an edge from I to j? That is, from I, can I reach the node j? If it is possible and j has not yet been visited, that is, j is not yet a key in the visited dictionary. If j was visited, it would immediately be a key because what is the first statement? Visited I true. So every time we visit a new node, we will make an entry in the visited dictionary, right? So two things I will check. That if there is an edge from I to j and if j has not been visited yet, right? So for that we have this is key function. We'll check that is j a key of visited dictionary. So if it is not, right, then this will return false. So not of false is true. So if both of these are true, then I will enter this if block. And inside visited dictionary, I will assign or call the DFS function recursively. So now I'm calling, so I know that from I to j I can reach. And j is not yet a vertex. That means I have to explore j now. See, think of it like this. This is our I, right? So from I to j, where are the edges that I have? For which j values I have edges? 1, 5, and 8.
5 and 8.
So first I want to explore this. So this is my current j. So what are the conditions I'm checking? Is there an edge from I to j? So this is correct. There is an edge. Another condition is what? That is j already explored? That is there an entry for j in the visited dictionary? No, right? I am just now exploring j. So both the conditions satisfy. So I will come here and inside visited, I will write DFS graph visited j. So now call this same procedure for node j. Okay. So let's say j is 1. So if I call this same procedure for 1, again, so now j is 1. That means here I have 1. So in visited dictionary, now an entry will be created for 1. So at this point, visited dictionary, I'm calling it V. Looks like 4 true, then 1 also true. Now for 1, you check that where all can I reach from 1. So in our diagram, we know from 1 I can go to 2 and 3. Right? So if I try to go to 2 first. So for each j in columns of graph, where the j will become 2, I will check that is there an edge from I to j, that is from 1 to 2 node. Is there an edge? Yes. Is 2 already a part of dictionary visited? Yes or
No,
no?
ma'am.
So is key will return what? False. Not of
False.
false is what? True. So both the conditions satisfied. So again now go inside. Yeah, tell me. I'm saying something. So again, here I will now call DFS graph visited J. Now what is J? I came from 4, I explored 1, then I came to 2. So what will I explore now? 2. 2. So now it is 2. So here also it becomes 2. Now visited I is set to true. That means there will be one more entry for 2 now. See, all of these nodes I have visited. Now check from 2 where all can I go. So for J in columns graph, check if graph ij equal to 1. That is, if there is an edge from 2 to some particular node. So 2 to 3 I have an edge, right? For that, this will
Yes,
be
ma'am.
correct. And is 3 already present in visited dictionary? No.
No.
So is key visited 3 will return false, not of false is true. So both conditions satisfy. So again come here. Again call this recursive procedure. Now J is what?
3.
3. Okay. So J is now 3. Now if J becomes 3, so there will be one more entry for 3 now. So 3 true. So for each J in columns of graph. So now tell me from 3, is there any edge? Okay, is there any node that I can reach from 3 which has not been visited?
No.
No, ma'am.
No, ma'am.
So which part of this will be false? This will be true. There are edges from 3. But this will not be true.
Not key.
Is key will return true. Because any node that I can go from 3, that I can visit from 3 has already been visited. So is key will return true. Not of true is false. So this if
False.
condition will never evaluate to true. So what will I do? Go back to the last recursive call. Right. What was the last call? Where J was 2. That was the last call. Right. From 2 only
Ma'am,
I
could you repeat the last step? After setting its, if not, is key is true, then what did you
Yeah.
do?
See, here I set a key for 3, right? Because I am currently visiting 3. So 3 is true. I have visited 3. Now I will check that what all nodes can I visit from 3. So tell me what all nodes are visitable from 3.
None of
2
them.
and, 2 and 1 I can
2
visit,
and
right?
1.
But
Yes,
they
ma'am.
have
Yeah,
already
yes,
been visited.
they have all.
That means
Yes.
there are entry for 1 and 2 in visited dictionary. So there are already keys in the visited dictionary, right? So this part of the if statement, not of is key visited J. That means any node J that I can visit from 3, there will be no such node that is not a key of visited dictionary, right? All the nodes have been visited that I can visit from 3. So from 3, I can go to 2 and 1, which are already visited. So if I write 2 here, visited, comma 2. So 2 is a key of visited, right? See, 2 is present here.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
So this is key part will return what? True. It is
True.
a key. Now not of true is false. So this part entire if will evaluate to false because there is an and statement here. So now what will I do? If it evaluates to false always, then I have to go back to the last recursive call, right? So what was the last recursive call? For node 2, from 2 only I came to 3, right?
Ma'am, it is telling return visited, right, ma'am?
But
If,
I cannot enter this part because if condition is not evaluating to true. This is inside the if. This visited equals to DFS.
yes, ma'am, it is false, right? Then after after it's setting to false, if statement, we'll go to the next step, which is below is return visited, right?
But no, this won't happen. Now I have to recursively trace back first. I will issue the return statement when I'm done with all the trace back. So once this doesn't work, then I cannot enter this because I have already visited all the nodes that I can from 3. So I have to trace back to the previous node from where I came to 3. So I came from 2 to 3. Right. This is how I was doing in the DFS algo also. So once I saw that 3 has been exhausted, so I traced back to 2 where I came from. Then I will again check that from 2, have I exhausted everything or can I still go to some new neighbor. See, I will explain this part again.
I got it, ma'am. No problem.
Ma'am,
Okay.
Look, why this is happening?
in this code, we don't have any logic for trace backing now.
No, it will trace back like, wait, don't know if they have written it here.
In the pseudocode, we don't have now.
They haven't written it. Yeah, but the logic here is that
In previously also it's not written, I guess, ma'am. Like in
it's not
recursive.
written. Since we won't ask you to write the code because this is a difficult code to write, so I think that's why they haven't written it. But the logic is that whenever we come across such a node I, okay, which has been visited, and all its neighbors have also been visited, for that node, this if statement will always evaluate to false. So I cannot proceed with the function. So I have to trace back to the last call of DFS. So last call for 3 was what? 2. So from 2, is there any more neighbor that I have not visited yet?
No.
Everything has been visited. So 2 again has to trace back to its previous call, which was node 1.
1.
So node 1 also has exhausted all its neighbors. So it will again trace back to 4. So see, this procedure, if you have understood how it works, I will actually explain this part. Okay, this will clear it up better. Okay, so let's
Yes, ma'am.
come to this.
Understood the procedure.
Right. So procedure, you got it. Now see this part. I will again erase all of this. Okay. So let's do it from the beginning. Yes, tell me. Anyone who didn't get it.
Ma'am, I think in this procedure we don't have any trace back, but I think so that as we are using recursion here, so this
Yeah, see
iterate,
here actually that base case is not written. Now here the base case is when everything is exhausted. That is the base case.
yeah. So this will iterate through the all the parts of the column we have. So after it recursive things, we would eventually reach all the points.
Yes. So eventually, see, after this 2, then we trace back to 1, then we trace back to 4. Now for 4 again, we will find some vertices which haven't been visited. So we will explore those. So for when j or I again becomes 4 here, then for 4 we will find some j values which have not been visited. Right? So we explored this part. But these neighbors have not yet been visited, 5 and 8. So when I get j as 5, so is there an edge from 4 to 5? Yes. Has 5 been visited? Is 5 a part of visited dictionary? No. So this part also evaluates to true. So again, now I will explore 5. So this j will now become 5. Understood? Like this I will go. And every time something is exhausted, you trace back to the most recent call. This will make it more clear. See this part.
Yes, ma'am.
Initially visited dictionary is empty. Okay. Now I am starting from node 4. So DFS graph visited 4. Graph is the graph, this graph that we have. Visited is empty and I'm starting from node 4. Okay.
So the final call will be the 4 only, no? Because we started from
Yes.
Chrome
It will
after
come back
we
to 4.
the final
It will come
last
back to
final,
4.
right?
Yes. Last call will
Okay,
also come back to 4 only.
4
But
only.
then
Okay.
that if condition will evaluate to false because there will be no such node that we haven't visited. All of them will be present in visited dictionary.
Okay.
So we can then return, end the procedure. Okay, then if you return visited dictionary, see visited is the dictionary that we are returning in the return statement. So
Ma'am,
once you
could you
return,
explain the second page, ma'am? Once
yeah,
again.
I'll come to that. See, the point of this pseudocode is that we will return visited dictionary when we have visited all the nodes. So that when you go to this dictionary and you ask for the keys of the dictionary, it should give you a key list of all nodes in the graph. That means I have visited all nodes using DFS. See, first I am starting from 4, right? So DFS procedure is called with the graph as argument, visited dictionary which is empty initially, and 4. That is the first node that we are exploring. So from 4, I can go to 1, 5, and 8, right? So I decide to go to 1 first. Okay. So 4 is visited, 1 is visited. So currently, when I visited 4, visited dictionary, there was an entry made in it, right? 4, true. Every time we visit a new node, an entry will be made. So now I decided to visit 1. Okay. So see, another entry for 1 is made. From 1, I can go to 2 or 3. So I decide to go to 2. So next page, see, another entry for 2 is made. Now, DFS graph visited 2. So another entry for 2 is made. From 2, I can go where? 4, 1 and 2 are visited. 2, I can go to 3, which is not yet visited. So DFS graph visited 3. At this point, the visited dictionary contains these 3 values. Okay. And we will add one more entry for 3. So now it will be 3 true. So this. Now from 3, I cannot go anywhere else. All of them are visited. Right? So what will I do? Trace back to 4. So
Yes.
4 I went to 1, from 1 I went to 2, from 2 I went to 3. 3 is all exhausted. So first you trace back to 2. 2 is also exhausted. Then you trace back to 1. 1 is also exhausted. Then you trace back to 4 again. So from 4 next I can go to 5 or 8. So I decide to go to 5. At this point, the dictionary contains the information of all the nodes that I have visited so far. So 4, 1, 2, 3. Next call is DFS graph visited 5. So now I'm exploring 5. And visited dictionary looks like this currently. So now I will form one more entry in the visited dictionary for node 5. Right? So it will look like this. So now what all nodes are visited? All of these. Now from 5, I can go to 6 or 7. So I decide to go to 6. So next DFS call will be graph visited 6. Whichever node you are exploring currently or you want to explore now, that will be passed as argument. Okay. So I want to explore 6. So 6 is passed as argument. This is the current visited dictionary. As soon as I make this call, the first thing I will do is I will create an entry for 6 in the visited dictionary because now I'm exploring 6. So there is an entry for 6 now. So now all of these nodes are visited. Now from 6, I can go to 7, right? Or 9 or 8. Any of these I can go to. So I decide to go to 7. So DFS graph visited 7. One more entry for 7 here. So 7 through. 7 through. So now from 7, where can I go? Anything that I can go to that is not visited. These are the visited nodes.
Ma'am, can we say that visited is recorded and at the end it is being returned, right?
Yes, visited will return the list of all the nodes.
Okay, yes,
But
ma'am.
our goal is that using BFS or DFS, we want to visit all the nodes in the graph. So if you have done the procedure correctly, then at the end, when I return visited dictionary, it should give you all the nodes. So when I come to 7, from 7, can I visit any other nodes which have not been visited yet?
No.
So trace back to where? 6.
6
That is the
and 5 and 4.
last recursive call. Now from 6, where can I go? That has not been visited yet. 8 or 9.
8 and 9.
Right? So next call, if I want to go to 8 first. So DFS graph visited 8. Right? So make an entry for
Ma'am, 1
8.
second. So from 6 we have done, again we have to go back 5 and 4. Again we have to 4 from 4 to 8,
No,
right?
once you exhaust everything from 6, then you will go back to 5.
Okay, ma'am.
Okay. So first explore one node completely. So 6,
Okay.
from there I can go to 8. So this is the next node. I can also go to 9. You can also take 9 first. That is also okay.
Yes, yes.
Any order you can do. So I did 8. So there will be an entry for 8 in visited now. That is 8 has been visited. Now from 8, where can I go? That has not been visited.
9.
9. So DFS 9. DFS graph visited 9. So for 9 also we make an entry in visited dictionary. Now from 9, where can I go? 10.
10.
So DFS graph visited 10. Okay. And you make an entry for 10. Now from 10, can I go anywhere that has not been visited?
No, ma'am.
So you will trace back to 9 here. From 9 also everything has been exhausted. So you will trace back to 8. From 8 you will trace back to 6.
6.
From 6 you will trace back to 5. And ultimately from 5 we will trace back again to 4, and 4 is also now exhausted. So all of these are done. Okay. So is it DFS clear for everyone? See, we
Yes,
won't
ma'am.
ask you to write the code, okay? Just have to understand how DFS works.
Yes, ma'am.
Hey, ma'am, I have a small doubt. Ma'am,
Yeah.
in the code that is given for DFS, like we are not mentioning about retracing back to the values.
Yes, that is not mentioned here because we are not actually interested in writing the whole pseudocode for this. Because this is a long procedure, okay? And it is actually difficult to write it using just pseudocode. If see, if I could write this in C programming or Python or anything, then I can give you the entire code for it. Okay. But for pseudocode, it is a little difficult to write because what will I write as the base case? Base case is when everything is exhausted. You cannot write that in pseudocode language, right? So for
So
that,
it
you
is
have to check.
understood.
Yeah.
We are
So that's
actually
why I
assuming.
explained this first, that when you see that for a particular node, this if will never evaluate to true, that is, everything has been visited that I can visit from a particular node, then you have to trace back. That is the base case. So this if condition that we have, this is base condition. Okay. So when this is all exhausted, so when this if will return false for every j value for a particular I, then we know that okay, that I value has been completely explored. So I have to go back to the last recent call. So that entire code is obviously not written. This is just a little procedure that they have written.
Will it give in the question, right?
That's
Sorry.
Will it give in the question of this understood? We have to go back.
No. See, from DFS, what type of question you'll get? Not, I won't say you will get any code from DFS. Okay, maybe the graph will be given to you. Maybe you can ask that from this vertex, which all vertices can you go to? Or what will be the last recent trace back, like this. So if I start from this vertex, which will be the last trace back after I have explored? So you can see the PYQs, you will get some idea. Okay. From DFS, not many questions are asked. Maybe one question you can have in end term. That's it. Okay, but when you actually learn some programming language like C, if you start with C, then you can find there are very nice codes for this BFS, DFS, all of these algorithms. Okay, there it can be easily written. But in case of pseudocode, it is a little difficult to write these things because pseudocode is just English language, right? Cannot write every
Yes.
logic using that. So
Understood.
DFS is
Thank you.
clear.
so that means, ma'am, in DFS we are actually keeping track of the total number of nodes that are present in our graph.
What you have to keep track of is that till this point, that is whatever point I'm at now, till this point, what all nodes have been visited. So for that, we have the visited dictionary. That's why every time we are visiting a new node, we are creating an entry. So I note that this node has been already visited. Okay.
Okay. Ma'am, that means this basically this visited dictionary, this doesn't tell us the relation between nodes. It is basically that what are not
No, it's
nodes
not
I have
about
visited.
relation. It is just what all I have visited till now.
Okay.
Okay.
Ma'am, then we have in DFS like 4 is an important connection. Like if there is no connection between 4 and 1, it uh, the total graph is disconnected, right?
Right,
Like
right.
can
So
we know?
disconnected graph, you cannot perform DFS. Okay.
No, I'm
Any
asking, can
disconnected
we
graph.
find out such like 4 is an important point? Like any other like is it not possible from this code?
No. See,
Like
you can start from any point. Okay, if it is a connected graph, you can start from any point. It doesn't matter. I can also start from 3.
no, ma'am,
That
I'm
will also
telling
work.
like the visited dictionary is only giving about if we have checked that
Yeah, no, that
node
information
or
you
not.
cannot get. That 4 is a
Okay.
significant node with connections.
That's
Yeah.
what I was asking. Yeah, okay.
So if we keep a track of how many times I am retracing back to 4, that will give you that information. That if I come the maximum time I'm coming back to 4, that means 4 is the most connected node here.
Ma'am, how can we keep track of that particular
That
security?
is very difficult to implement.
Ma'am, could you repeat what did you say? Just
Yeah, I said that, see,
oh,
if it is an important node that is connected to a lot of other nodes, that means I will come back or trace back to that node a lot of times, right? Because from there I am going to a
okay,
lot of
understood.
neighbors.
Got it, ma'am.
Yeah. So
Okay.
if there is a way that is every time we trace back, if we keep a count variable and increment that, then you can tell that, okay, this node for this count is high. That means this is a well connected node. Okay, so let's start practice assignment. Is visible?
Yes, ma'am.
Okay, only 7 questions are there. Okay. So now that you have understood what is recursion, this will be very easy to solve. Like, this is the unique procedure. Okay. So here what we are trying to do is it will take a list as an input. Okay, and it will return the unique elements in the list after removing the duplicates. So consider that the list has some duplicate elements. If it doesn't have any duplicate, then it will return the list itself. But if it has some duplicates, it will remove the duplicates and only give you the unique elements in the list. Okay, that is what this code does. So we have to fill in this part of the code that is not given. Okay. Now, see what the rest of the code is. Let's say I have a list 13135. Okay, this is the L that I'm passing. So according to this procedure, what it should return is 135. Only the unique elements, right? This should be the ultimate return value.
Yes, ma'am.
Yes,
So
ma'am.
this list I am taking as input. Now I will have an empty list called init elements. Okay, this is an empty list. So if length of L is less than or equal to 1, this is base case. When length reaches 1, I will return the list. If not, okay, then come to this line. So init elements is another variable in which you will store init of L. So if I start with this procedure, so I will tell you that this is the correct code. Okay, but let's understand why this is correct code. So if I take this list as input, what is the length? 5,
5.
which is not less than 1. So come to this line 6. So init element will be storing what? Init of L, that means
Initial part.
313.
1, 3.
Sorry.
1313. Okay. Now in this code check, option D. Next line is if member init elements last of L. Okay. So what is last of L here? 5. So is 5 a member of this list? Yes or no?
No.
No, ma'am.
So this will return false. 5 is not a member. So come to the else part. Return unique elements append last of L. So what is the recursive call here? This one, unique elements, unique init elements. This is the recursive call, right? So control will shift here. So this part is now what? Unique. What is the argument that is passed? 1313. Right. So this is the first return statement. So that will be unique 1313 plus what is the last of L? 5. Up to this it is clear? Anyone? Issue? Okay. So now control shifts here. The same procedure you will do now for this list 1313. So go here. What is the length of 1313? 4. So base case not satisfied. Again, init elements. So now init elements will be what?
131.
131. And what is the last of L?
3.
3. Last of L is 3. So again come to this code. So is 3 a member of 131? Yes,
Yes,
it
ma'am.
is. So I will issue this return statement. This is the second return call. So unique init elements, that is 131. Now for this list, again, go back here. So what is the length of 131? 3. That is not less than 1. So base case not satisfied. Again, init elements. So now init elements will be what?
1, 3.
1, 3.
1, 3. What is the last of L?
1.
1.
3. Last
This
of.
one. This one. No? This is
Okay,
the
okay.
argument.
Yes.
Okay. This is the L. So last of L is 1. Again, come back to this part. So in 1, 3, is 1 an element? Yes. So again, return statement is issued. This is the third return statement. So that will be unique 1, 3. Right? Again, go back to this code. So this L is now 1, 3. What is the length? 2, not less than 1. So again, init elements. Now init elements is what? What is the list?
1.
Just 1. And what is last of L?
3.
3. So now again go back. So 1 is the list and the element is 3. So is 3 present in this list? No. Right? So come to else part. This is the fourth return call. So unique init elements will now have just 1 and append last is 3. Right? For this call the last was 3. This element.
Yes, sir.
Now again control shifts here. Unique 1. So what is the length of this list? 1. So is the base case satisfied? This base case, is it
Yes, ma'am.
satisfied? If L is 1, it is satisfying, right? So what will it return? L itself, that means
List
1.
of 1.
Where is this value returning? To the last recursive call, that is the fourth call. So this unique, this part will return list 1. Right? Agreed? Anyone who didn't understand this part, tell me. So now I will append 3 with this. So after appending, what will the list look like? 1, 3. Correct? This 1, 3 will be returned where? Third call. That means here. So here nothing is appended. So this will just be 1, 3 only. Again, this 1, 3 will be returned where?
Second return
Second
statement.
call. Here also nothing is appended. So 1, 3 remains. Again, this will be returned to first return
First
statement.
return statement.
So that means here it is returned. So 1, 3. And you have to append 5. So after appending, it becomes 1, 3, 5. So this will be returned as the final value. That is all the unique elements. Is this clear? Anyone who didn't get it, raise your hand or tell me. Everyone understood?
Yes,
Repeat
Understood,
once.
right? Repeat.
I got lost connection.
So up to which part did you see? The fourth call, did you understand?
Oh, no, one, just 2-3 minutes back. From first only. First,
First call.
second.
So here, okay. So here the control
Just,
shifts to this unique
just orally
statement.
explain, no issue.
Yeah, see, this unique statement here the call will shift, right? Control will shift. So again, go back to the unique procedure here. So now L is what? 1313. Length is 4. So base case is not satisfied. Init elements will give this. Remove the last element. So 131. Right?
Okay.
Last is 3. So now come to this one again. Check, is 3 a member of 131? 3 is a member of 131.
Yeah.
Right? So issue the second return statement, this one. So unique init elements, that means unique 131. So again, come back to the parent this procedure, unique procedure. So now L is 131. Okay, length is 3. That means again base case not satisfied. So go to init elements, init of L. So if I do init of L, now I will get 1 and 3, right?
Yes, ma'am. Yeah.
Last is 1. Now go to this one again. Check is 1 a part of this list, a member of 1, 3. Yes. So again return unique elements with 1, 3 as the argument. That is this third call. Again go to unique procedure. So 1, 3 is now the list. What is the length? 2. Base condition not satisfied. Again go to init elements. So now init elements will be what? This
1,
just 1. And last element is 3.
3.
So again check here. Is 3 a part of the list 1? No. So come to else part and do the last fourth return statement. So unique 1 plus 3. So when I do this unique 1, now control shifted to unique 1. So what is the length of this list? 1. Length is 1. So that means base condition is satisfied, right? Length is less than equal to 1.
Yes.
So I will return the list itself, that is 1. It will be returned where? In the last recursive call, that is the fourth call. So here, this part will return 1. And I have append 3. So after I append 3, this will be the list, right? 1, 3. So this will be
Yes,
returned where? To the third call. That is here. Third return statement. But here nothing is appended, so 1, 3 will remain. So 1, 3 will again be returned to where? The second call, where again nothing is appended. So it will remain 1, 3. Now you will return this to the first call here. So this unique 1, 3, 1, 3 ultimately evaluates to just 1 and 3. And I have to append what? 5. So ultimately 1, 3, 5 is the list that will come as the final return value. Clear?
Yes, ma'am. Got it.
Okay. So for this question, this is the answer. Okay. Please check the other options also. I'm just trying to go through all the questions. So go through the other options. Something will be wrong. Okay. Like just check once. Here, what is wrong? If member init elements. So here it is writing just init elements, not calling the unique procedure, right? So this line is wrong. You have to write unique init elements. Here also, same mistake is there. I think option B and C are single. No, here this is also wrong. Unique is not being called anywhere. So no recursive call. So these two options are wrong. Option A, what is wrong? What is wrong in option A? It is looking same only, no? Same
Ma'am,
option.
actually the last means we are
Last is
not
a different.
appending list, right?
Appending.
Plus plus
Oh,
last.
okay, okay. This is not in the
Yeah,
form of a list.
brackets. Yeah.
Right, right. The third brackets are missing. Right. So these three options are wrong. Now come to question 2. This is a very easy question. Everyone knows palindrome, right? Palindrome means something that reads the same from forward as well as backward. So madam is one such word. So if you read from here MADAM, if you read from back also MADAM. These are palindrome words. So this procedure is trying to do what? So if X is a row in the words table, that means a row in the words table contains what? A particular word, right? So at the
Yes,
end
ma'am.
of the procedure, flag will store true if the word X or the word present in row X is a palindrome. Then flag will be true. Otherwise, it will be false. Okay, this is what we are trying to do. So we have to select the correct implementation of the is palindrome procedure. Okay, so what code is given to us? Word list is empty list. Flag is initially false. Word list equals to explode x dot word. What does this explode do?
Scatter all the words, the letters.
Right, extract all the words from the word, right? In the form of a list. That flag is a variable inside which we are calling the isPalindrome procedure with word list as the argument. So we have to write the code for isPalindrome. Check option A. 1 second. See, option A is palindrome procedure. Okay. This list is the argument. So this is the word list, basically whatever explode returned. So let's say madam is the word. So word list will look like this. Right? So what is the length of this list?
5.
5. So what is the first condition? If length is less than equal to 1. So this is not true. So come to the next step. First of L is not equal to last of L. Is this correct?
No,
Both
ma'am.
are M. That means I won't return false. So come to the else part. You will return is palindrome. So this is the recursive call. Is palindrome inside it? What is the argument that we are passing? So since I have already checked for the first and the last letters, so I will remove them. So init of rest of L, or you can also write rest of init of L. Same thing. I'm just removing the first and the last elements. So here this will be passed as argument. Up to this, everyone get it? Clear?
Yes, ma'am.
Yes, ma'am.
So next again call the same procedure. So now L is this ADA. Length is what? 3.
3.
Not less than 1, less than equal to 1. Again, first of L is not equal to last of L. Is that true? No. First of L and last of L are same. So come to else part, return. Again call the recursive call is palindrome. Right. So again now you will do init of rest of L. So what will be the argument? Just D. This and this are removed. Okay. So now what is the length? 1.
1.
So this base case is now satisfied. So return true. Right. Where is this return true going? To the last recursive call. So
Yes,
since
ma'am.
there is actually nothing we are doing here, right? So this true value will keep on tracing back until we reach where the procedure was called first. That is inside this flag. So the true will come to the flag direct. So if flag is true, that means we know that it is a palindrome. So madam is a palindrome and this correctly gives the result. So option A is correct. But this is an MSQ. So option B also check. So if the same thing we are doing here, what are we checking? That length is equal to 1, fine. If length is 1, then we will return true.
True, ma'am. This is also true.
Like clearly see. If first and last are equal, right? Then it is saying that return palindrome. Okay, else return false. So if I take that same thing, right? I'm just going to explain all the options here because this question a lot of people got wrong last time. So is palindrome, this is the list. So length of L is 1, no. Length is 5. So come to this if first and last are same, yes. So return is palindrome init rest of L. That means these two are removed. So here now it is ADA. Okay. Again check. So ADA length is 3. Length is 1, no. So come to next if first and last are same, yes. So return. Now what will be the argument? Just D. Right? Rest and init will remove these two. So now length is 1. It will return true. Right? So again, this is correct. But as far as I remember, this one was wrong.
Ma'am, once could you show option C?
Something is wrong.
Uh,
Wait.
I
This
I
is
guess else
wrong.
should be a bit inside. Else part.
Else should be inside
Y-
this if the indentation is wrong here.
Yes, ma'am. That might be wrong. We have to check
Wait,
option C,
wait,
ma'am,
wait,
for that.
wait. But this if else is also indented here. No, indentation is okay here. What is wrong then? Length we are checking. Just here the less than equal to is not given. Equal to is given. But that will also work. If
Ma'am,
first
last
of all,
return false last.
this you're saying,
Yes,
Uh,
ma'am.
so this will
ma'am,
return false, right? So
ma'am, I
anytime this
guess it
one,
should be compulsory written less than or equal to 1 because sometimes empty list might
sometimes
be
if it is
present.
an even, if it is an
Yes,
even
ma'am, that's what I was
palindrome,
telling.
then the
Yes,
list
ma'am.
will be less than equal to. Correct. So
0.
this should be less
That
than
time.
equal to.
That time
Right.
it will be false. Option B
Like
would be false.
if we say any word that is an even palindrome. Let's say if we check, just I'm giving a makeup word. Okay. Let's say I'm giving KOOK. This is an even palindrome, right? So for this, if I check in this procedure, see, it will not return the correct thing. Why? Because first the length is L. Okay. Explode will return this, right? So length is 4. So this doesn't satisfy, but first and last are equal. So you will go to recursive part and this will be just O and O because init and rest will remove these two. Okay, so now the length becomes 2. So length is again not 1. So it will come to this line again. So first and last are again equal. But if I remove with rest and init, then this will become an empty list now, right? Because rest and init will remove both of these. So this becomes empty list. Now empty list means what? Length is 0. But see, there is no provision for 0 here. So the base case will never be satisfied. So nothing will happen. This will return false. Because base case is not satisfied. Again, first is equal to last. There is no element. So I cannot check this. So this will evaluate to false. It will come to the else part and return false. So this code will not work for even palindromes. Okay. So B is wrong. Now C is correct. See, here the less than equal to is there. Only what we have changed is that here previously in option A we were checking that is first of L not equal to last of L, right? That we were checking here. If not equal, then return false. So here just it has been reversed. So if it is equal, then return this, otherwise false. So it is very similar to your option 2, except here the less than equal to provision is there. That means this is the correct code. This will give for even as well as odd palindrome. So option C is also correct. Let's see why D is not working. So here less than equal to is fine. So, okay, here the recursive call is in the wrong place. So if first and last are same, then you should return the recursive statement here. Instead, it is returning true here. That means if I, let's say, have a some, give me some word which has the first and last letter as same, but it is not a palindrome.
Cook, ma'am. COOK.
But there the first and last letters are not same.
Modem.
Modem. Good. Modem is one such word. So here the first and last one is same, right? So this condition will be satisfied and it will directly return true to flag. So even if it is not a palindrome, it will still return true. So this is the wrong code. A and C are correct. Is this clear, everyone?
Ma'am, once could you show option D?
See.
Okay, it's returning true before even confirming, right? You are telling.
Yes, because the this
Okay.
recursive call is
Before
in the
checking
else part.
till the last, we are initially we are initializing to true.
Right.
Okay.
Basically, this will never return false. There is no return false statement. So for all the things or every word that you give, at some point it will return true. So see this code, look at it very carefully, okay? Because all the rest of the questions are based on this one. So I will give you 2 minutes. Okay, now it is 58. So till 8 o'clock, just go through this code and tell me, is there any particular mathematical operation that you can think of that this code represents? Okay, just take 2 minutes and study the code. Anyone got it?
Ma'am, we are just calculating the difference, ma'am.
So what is this going to return? If I put any two numbers A and B, which are positive integers, what is the return value actually representing? Ultimately, the answer will be the second return B, right? At some point, it has to come back to return B because all of the rest are recursive calls.
Mm,
So what is
ma'am,
that B?
it's not like compulsory that B should be equal to A, right? Sometimes.
No, it's not compulsory.
Then we won't be getting B every time, right? ma'am?
See, there will be some difference. Okay, that we will be calculating. So A and B will be changed. See, when the recursive call, once you calculate the difference in the recursive call, then it becomes B comma difference or A comma difference. Oh, sorry, difference comma B. So A is replaced with this difference thing, right? But ultimately, return value will be the B value. So return B.
This
So
will
what is
be
this?
this will go in with the infinity, na? I think.
This code will return your HCF of the two numbers A and B. Okay, this will give you the highest common factor. See how this works. So calculate A comma B. Okay, let's take any two numbers, 10 and 15, let's say. So what is the HCF of 10 and 15?
5.
5 is the HCF. So this code should give you that. See, difference is initially 0. If A is less than B, so 10 is less than 15. So return calculate B comma A. First, this is the first recursive call. So calculate B comma A, that means here calculate what will be the argument? 15 comma 10. Right, just reversed it. Now for 15 comma 10 check here. Now A is 15, B is 10. So difference is still 0. So now is 15 less than 10? This A less than B you are checking. Is 15 less than 10? No.
No, ma'am.
So come to the next if. Is 15 equals to 10?
No.
No. So now calculate the difference. How much is 15 minus 10? That is 5. Now come to this if. Is the difference greater than B? So what is B value? 10. Difference is 5. Is the difference greater?
No.
No.
So come to else part. So return, this is the second recursive call. Calculate B comma difference. Okay, this was
10
the
comma
first
5.
call. This is
10,
the second call. So B is what in our current one? 10.
10.
And difference is 5. So again, check for this 10 comma 5. So now
5 comma 5 and it return B.
right.
10
So
minus
A
5 is
will
5.
become 10, B will become 5. Now is A less than B? No. So come to this part. Is A equal to B? No. What is the difference between A and B? 5 again. 10 minus 5 is 5. Is the difference greater than B? Is 5 greater than 5? No. Come to else part. So calculate B comma difference. So B is 5. That means third recursive call will be calculate 5 comma
5,
5.
5.
So here, what condition will satisfy? This if A equals to B, right?
Yes, ma'am.
Yes, ma'am.
Here what happens? A and B are now both 5. So A less than B is not satisfying, but A equals to B is satisfying. What am I returning? The B value. That is 5. So this is the HCF. Got it?
Yes,
So what are the questions? See. So if you understood that what this code is doing, then you don't even have to go back to the code. See, what is the return value of calculate 12 comma 3? What is the highest common factor? 3.
3.
3.
So answer is what? C. 3. You know that it is calculating HCF. You don't have to go back to the code. If someone doesn't understand, then they would have to check with this 12 comma 3 value
Ma'am,
here.
if we do it for prime numbers, that will be returning 1.
Yes. For prime numbers, always the highest common factor is 1 only, right?
Yes, ma'am. Ma'am, could you do it for 7 and 5? Just
Yeah, for
like I
7
want.
and 5, if I do, see, no problem. A is 7, B is 5. Okay. So is A less than B? No. Is A equal to B? No. So take the difference. Difference is what? 2. Is difference greater than B? No. So come
No,
to
ma'am.
else part. So calculate difference, that is 2. I'm sorry, B, what is B? 5. B comma difference. So 5 comma 2. Right now do for 5 comma 2. So now B is 2 and A is 5. So is A less than B? No. Is A equal to B? No. Again calculate the difference. So what is difference between 5 and 2? 3.
3.
So is 3 greater than 2? Yes. So calculate difference
Yes.
comma B. So now the procedure call will be 3 comma 2. Now A is 3, B is 2. Is A less than B? No. A equal to B? No. Again calculate difference. 3 minus 2 is 1. Is difference greater than B? Yes. No. 1 is not greater than 2. So go to else part. So calculate 2 comma 1. Now come here again. Now A is 2, B is 1. Is A less than B? No. Is A equal to B? No. Again calculate difference. So 2 minus 1 is giving 1.
1.
So is the difference greater than B? No. So I come to else part. So calculate 1 comma 1. So this statement will return true and B is 1. So for prime numbers, 1 will always be the HCF. Got it?
Yes, ma'am.
Okay. So see, if you understand that this code is doing HCF, then you don't need to check for every value that is given in the question, right? You can just look at this 12 comma 3 and you know HCF is what? 3. Then next question is, what is the return value of 14 comma 17? So 17 is a prime
1.
number.
1.
So 1.
1.
See, the question that you asked only. So 1.
Ma'am, like you have solved many times, then you got to know it's one. Like it's returning HCF, or like directly you understood it is returning HCF. Like,
No, I know this. I have done this question before also. So I knew
okay,
that this was the code for HCF.
okay. Like by looking at the pseudocode, we can't tell, right? It's
No, you
HCF or
can
not.
tell if your arithmetic knowledge is clear. If you know how we find HCF, then you will be able to relate. Okay. That's why I gave you the first 2 minutes to see if you can relate that this is the code for HCF. Anyways, whenever you learn a new programming language, these are the basic programs that we learn. Okay, HCF, LCM, how to find these things, or how to write for prime number, composite number, how to check. These things we learn. Okay, so when you are learning a programming language, these things will come more easier to you. Anyways, if you don't understand that it is HCF, then you just have to check with the values. That is also not going to take much time. Okay, this is an easy code. Then this question is asking how many times is the procedure calculate called in order to compute 14 comma 17. See, here you have to do the whole thing. Here you cannot write using HCF. So you have to check how many calls are there. So 14 comma 17. See, you know what is a catch to understand that this is an HCF program? That every time you are finding the difference, next time you are calling it with the difference and the second number. So this is how we actually do HCF also. Okay, this is one hint. Okay. So for 14 and 17, so A is 14, B is 17. Now calculate how many times. Okay. So they have said, see this thing, include the first call in your answer. Okay. So difference is 0. Is A less than B? Yes. So now I have to call what? This is the first call. So this will be calculate 17 comma 14 now, right?
Yes, ma'am.
Now this 17 comma 14, when I go here, then again difference is 0. A is not less than B. A is not equal to B. Now calculate difference. 17 minus 14 will give you
3.
3. So is the difference greater than B? No. So come to else part. This is the second call. So calculate B comma difference. That means 14 comma
14,
3.
comma 3.
So for 14,3 also A is not less than B, not equal to B. Again calculate difference. 14 minus 3 is 11. So is difference greater than B? Yes. So third call. This will be 11, 3. Right? Now for 11, 3 again check. Again you have to calculate the difference. What is 11 minus 3? 8. So is 8 greater than 3? Yes. So fourth call. C. 8, 3. Right? Now for 8 and 3 again you have to find the difference. 5. Is difference greater than B? That is 5 greater than 3? Yes. So fifth call. C. 5, 3. Again find the difference. 5 minus 3 is 2. Difference 2, is it greater than 3? No. So go to else part. So sixth call. This will be B, 2. That is 3, 2. Again check. So this is not satisfying, this is not satisfying. Difference is 3 minus 2 is 1. So is the difference greater than B? That is 1 greater than 2? No. Come to else part. So seventh call. This is B, difference. That means 2, 1. Again check. This is not working, not working. Come to the difference part. So 2 minus 1 is 1. Okay, is difference greater than B? That is 1 greater than 1? No. So this part, else part. Eighth call. 1, 1. Right? Now 1, 1 for 1, 1 when you go evaluate this will return true. Now total you have called inside the procedure. How many times have you called the procedure? 8 times. But we have to take the original parent procedure also. That means total how many times? This
9
calculate
times.
procedure 9 times. This is the initial one. Okay, the 0th time. This also you have to calculate. So total 9 times. Answer should be here. It is 9. Okay. Last, second last. So for any two positive integers a and b, what does calculate a, b return? HCF of two numbers. Okay. So even if you don't understand from the code initially, once you solve this question 3 and 4, you will understand that it is the HCF, right? So you can write that.
Yes, ma'am.
Now last question is, what is the result of the following expression where a and b are two positive integers? So if calculate AB and calculate BA, I'm checking. Okay, that are these two procedures going to return the same thing?
Yes, ma'am.
So
Yes,
for
ma'am.
any two integers, no matter what order I take in, because I already saw that if somehow this happens, that A is less than B, then I am reversing it. I'm doing it B, A. So anyway, I'm reversing it. So no matter the order in which A and B are given in the argument, A, B and B, A will give you the same thing, right? So calculate A, B equals to calculate B, A will be true. These two are same. Okay, that's the last question. So any doubt from practice?
No, ma'am.
No, ma'am. No.
Okay, so only activity is left. So I'll tell you, sir, I think we'll take tomorrow's session. So activity questions and your that's 10.5, right?
Yes, yes.
So these
Yes,
two
ma'am.
things
We
I'll tell,
can.
sir.
Okay, ma'am. Thank you,
All
ma'am.
right. Yeah. Thanks for joining.
Thank you, ma'am. Good night.
Yeah. Thank you.
Thank you, ma'am.
Thanks.
Thank you, ma'am. Good night.
Yeah. Thank you.